Okay, so it's about mainly these levitated mechanical experiments. So you have heard about it yesterday in Markus Aspelmeyer's talk. Before I start, there will be some other little things I wanted to talk about. Maybe first to remind you where Southampton actually is. So there's London, and Southampton is there. So it's at the south coast. Yeah. It's still there. Yeah, exactly. Yeah. So because there was this question, what could be like a really big building project, yeah, for someone who's ambitious in building something. So I have two recommendations. First would be a wall, a border, yeah, 10-meter concrete floating on the water, and then if that's finished, a bridge, yeah, from Calais to Dover. Yeah? So something like that. This would be ambitious. So I don't know, Terry, if you're interested. I think Boris Johnson already discussed the bridge project, so I think they're looking for developers. Okay, good. So that's the location. We have done that. Before I talk about the mechanical things, I just wanted to also mention two other experiments where I have been somehow involved more at the fringe because we happen to have some expertise in, for instance, here in this case, so there's a metallic particle which is spinning. It's levitated, and now the question is, can you use this to test some, pretty old predictions, Zeldovich amplification? So what you try to do is I don't know if it's really some feedback. I hear myself quite loud. I don't know, it's okay for you? Yes, okay, good. Okay, so what you do is you use these coils here to generate a specific type of electromagnetic wave, which carries so-called optical angular momentum. So the polarization of this wave is twisted, it's spinning while the light is propagating, and you send this to the rotational object, to the metal sphere or cylinder, and if you fulfill a certain condition, then the light which comes back from the metal cylinder can be amplified in its amplitude. Yeah? So that's Zeldovich amplification. And the condition which you have to reach is that the spinning frequency has to be higher than the frequency of the wave. And so we wrote the proposal because we thought that's quite interesting that we can do it. It's mainly driven by Daniele Faccio from Glasgow. He's working on analog systems, and of course Bill Unruh told us about these type of experiments, and he is pushing for those experiments for a long time. And I just wanted to tell you the story because it's quite amazing. So that is quite unconventional physics, but we have been awarded an UK research grant from an official governmental funding agency because people like Bill, and there's a community in the UK, so Silke Weinfurtner and Ulf Leonard before her, and they pushed for these analog experiments, and now it is really possible to attract public funding to do this experiment. So that's interesting. Something which I considered to tell you, but I decided not to, is that we have actually done this experiment and we have seen amplification, but it's so brand new and so preliminary, and we have to convince ourselves that it is really the right effect and it's really Zeldovich amplification. I prefer to do it at a later conference. So that's an experiment which you can do, and you can test interesting physics there, and it also has to do with this levitated object. It has to do with rotation. Another experiment which also has to do with rotation, and which we did together again with Daniele Faccio and Miles Paget a couple of years ago, is to do a very classic quantum experiment, the Hong-Ou-Mandel interferometry, which is done on a rotating platform. And if you do this in rotation, then you generate some sort of acceleration. It's a non-inertial reference frame, and the question is if that has an effect on the quantum experiment which you're doing there. So we didn't see an effect in the experiment because the acceleration was not large enough, so it was not expected, but we could basically demonstrate that the trend is as expected. And again, I'm not the main guy driving this experiment, it's Daniele, and they're continuing this type of experiments. I just wanted to mention this, that it's not only these levitated optomechanical experiments, there's a whole class, or the different experiments where technology is now approaching a point where you can test new things. Okay, so let me go back to levitated mechanical systems, and I want to start with motivation, and I will basically show you yet another of those models where, of course, many of you can immediately say, yeah, they don't make sense, and what is it? So I will talk about collapse models. I spent quite a lot of time, actually almost 10 years, to think about how to test these models, and for me, as an experimentalist, the most important thing is that you can actually test them. So if they make sense or not, okay, but I get a prediction which I can test in an experiment against a different prediction from quantum mechanics. Okay, so we wrote this paper almost 10 years ago, which is a summary of literature, existing ideas, summarizing these models. It includes models which include or have something to do with gravity, gravitational decoherence, gravity-induced collapse, the Yoji model, Penrose model, these kind of things. And my part in this whole thing was to think about how can we test it? What is the experiment? And the end result is this here. So during my talk, I will come back to this plot. That's an exclusion plot. So people who do, I don't know, searches for dark matter or so, you have always these kind of plots where you plot some parameter, and then you can compare the model expectation against experimental results. And that's the same thing here. So you have a model parameter lambda and the model parameter RC of those collapse models, and all these colorful areas are different experiments. Yeah? So there are, for instance, also experiments like LIGO and LISA, Pathfinder. There is gamma ray emission, X-ray emission from germanium. There's optomechanical experiments, and I will basically take some time to show you what we have tested before. So you see that there are different models, so these black markers. So that is the GRW, Girardi-Rimini-Weber. That was the first collapse model, as you likely know, from the 1980s. That sits there, still untested, but we have tested some so-called CSL models with parameters suggested by Stephen Adler from Princeton. Okay, so now to show you the equations. And the first thing is I want to say is don't ask too many questions on those equations. I'm not an expert. I can likely not answer these questions. But that is how it looks like. So you can see it's, again, modifying Schrödinger equation. So the first part, and then there's all this stuff here, which is somehow reverse engineered to preserve certain features which are important. So for instance, the idea is here that you have this omega, no W is actually the right thing. So this dW, that's a noise, a white noise, which is affecting your superposition state, and it's kicking the superposition state. And when the kick is sufficient, then it's collapsing the wave function, right? There's M, which is a mass operator, which gives you mass dependency. So if you have a small mass in your system, like an, I don't know, electron or atom, then the collapse kick is not effective, and your superposition or your quantum state survives. Yeah? If you scale up the mass, if you make it more macroscopic, then that's not the case anymore, and the wave function collapses, and you get the classical state. Yeah? So that's the basic idea of these models. You have this random field, which is helping you to avoid faster than light signaling. That is one of the problems which were mentioned this morning in Schrödinger-Newton models, and that is fixed in those models exactly by the randomness of the field, which is doing the kick. It reproduces Born rule. Yeah? So if you run your quantum mechanical experiment like the double slit, you perfectly get the expected probabilities for the outcomes of your measurement. So in the end, what I'm telling you in details, and I for many years have avoided to say it in such a clear way, but basically tries to solve is the measurement problem. You have a dynamical equation which gives you two different dynamics depending on if the collapse happens or not. So I think it's interesting beyond testability that what you actually need is you need a classical background field. It has to be stochastic. It has to be nonlinear. So for instance, something like a gravitational wave or maybe some dark matter candidate could do the trick. Yeah? So the models per definition don't have any physics. It's just a mechanism to describe the kick. Okay. So now that's the wave function level. You can, of course, write it down on the level of density matrix. So that is like the master equation in Lindblad form. And then you have this gamma, which is written down for the collapse. And then that was one very early attempt, actually, from this review paper, where I tried to map for the first time somehow what the model predicts and how experiment can test it. So what you see here is basically a plot of this gamma function. And now the question is, what is a good experiment to test for these collapse models, for the effect of the collapse models? And you put in a length parameter, which is the size of your superposition. So the idea at this point was that, of course, the prototypical experiment to test this is matter wave interferometry. So you generate a spatial superposition state, and then you see how far you can push it in terms of size, mass, and time for the existence of the superposition state before the collapse kicks in. And that was a very important statement at the time, and of course it's a bit engineered. And the statement is that it wouldn't help you to try to do it with atoms because the mass is not high enough, even if you can do very large superposition sizes. It doesn't help you if you do it with very massive optomechanical systems because the superposition size is so small. But what is really good is to try to do it with these levitated mesoscopic systems, because there you tick the right parameter boxes, the right parameter space of mass, length scale, and time scale. Okay, so that's the motivation, that's these models. And then we'll come back and talk about how we have tested some parameter space with mechanical systems and with other experiments. There's, of course, to continue motivation, there's my version of the mass plot. So, looking at the interface of quantum mechanics and gravity. So Markus explained this. I will skip through this fast. This is our proposal how to look for a classical explanation of gravity. So what we basically follow is this idea of Feynman and others. So you generate a superposition state of a massive object. How does the gravitational field, or I don't know if you want GR, how the space-time looks like, which is generated by this by the superposition state. And now, if you run two different scenarios and you assume that the feature of gravity, of quantum gravity, is that the gravitational field or space-time can be in a superposition, and you call this the quantum scenario, and you assume on the other side that if gravity is classical, it cannot do that, then you get two completely different predictions for the same experiment. Again, it's an optomechanics experiment, and it's a very optimistic proposal, but we think that in the near future one could actually do the tests and then you would see it. There's the entangler. It was mentioned many times before. I co-authored one of the papers with regard to Bose. So again, because of interest in superposition, so what you actually have to do, according to the original proposals, you have to generate two of those massive superpositions. You have to run them parallel, and then you drop them, and then you allow for only gravitational interaction between these two parts of each superposition. And then if gravity is a quantum interaction, then the idea of this proposal is that you should see entanglement if you do like the right analysis of the correlations in these two interferometers. So it triggered a lot of discussion, and people say it's an influential paper. I don't know. Okay, so dark matter. Many people work on dark matter. Mechanical systems are interesting, of course, and that's another motivation to make really precise levitated mechanical systems and see for what type of interactions they're sensitive and if they can help to exclude or test for dark matter candidates. Gravity of two particles, Markus explained it yesterday. You can, again, think of different models, modified gravity or things like that, which would give you certain deviations if you could do the experiment. Also, that is, of course, a well-known story, and many people have worked on this over the years. yeah, so I will come back to this when I talk about superconducting levitation, because I think that's maybe a good platform to try to do it. Okay, so that was that's the motivation part. Now for the experiment, so for some reason which is not really, it was not intentional, but for some reason we ended up to actually do all three of these experiments in Southampton, so optical levitation, magnetic levitation, and ion trapping in a Paul trap of these mesoscopic particles. And as I said, the first objective for these experiments is to control the system so nicely that you can generate some sort of non-classical state. So it could be a superposition state, but there are also other ideas for non-classical features in those mechanical states. So from the conceptual point of view, so now you have this, you have decided you want to go for this type of physics, you want to test quantum mechanics and gravity separately or maybe at the same time if you can. And then you say, okay, I do it with these levitated systems, mesoscopic, 100 nanometer, micrometer in diameter, that's like the size scale, and then you have to choose what type of experiment you want to do. And I would separate this in two classes. So one is what we call interferometry tests, and that is indeed matter wave interferometry. And here you see a version of this. There are many other ideas in the community, but that's our way to do it, or try to do it, is to really do an almost one-to-one version of the double slit experiment, where you have a source, a grating, and a detector. So you first trap your particle, you cool it, you prepare the initial state, you drop it through a phase grating, and then you detect the position. Then you repeat this many times, and you should see an interference pattern. So again, the timescales are interesting. So in 2014, we basically wrote this proposal, and we said, okay, so if you use the same tricks which are used for molecular interferometry, so you do it in the near field, you can relax a little bit the cooling requirements. Then for a 20 nanometer particle, so that's 1 million or so atomic mass units, you can actually do this at room temperature. You don't need to cool the internal temperature of the particle, and the interferometer would be of something like this. Yeah. So you see the length scales there. Then we started to do it. So we have done basically the first part, which is trapping and cooling. So you see some stuff there. I don't go too much into detail of this technical stuff. What basically happened is it was early days in levitated optomechanics. It's a new system. It's a very clean harmonic oscillator, which you suddenly have in the lab. And then, of course, you start to play, and then you almost forget what you wanted to do because there's so many things. So we did cooling. We did detecting forces at surfaces. We looked at rotation of non-spherical particles. We looked at, sensing of, electric fields, magnetic fields, these kind of things. We applied Kalman filters, and we also did some squashing. So we basically tried to manipulate the motional state in phase space in a specific way. So that's just a snapshot of the things we were trying to do. So for the interferometer story, we are basically, I would optimistically say, 2 years. Yeah? So we have basically the cooling. We have now started to implement the grating, and we will do it in a slightly different version than what I have shown you on the previous slide. But I think that for like a small nanoparticle, we should be able to run the first experiment and then hopefully achieve superposition in a couple of years. Okay, so then, and that refers again to the context of testing these collapse models, is now if you have these particles trapped in harmonic traps, you can also do what we call non-interferometric tests. So you can actually look directly for the noise, which is predicted to be an important ingredient of these collapse models. The first idea of looking for the noise was, at least for me, there's of course a longer history, and other people have looked at this before. But all the work I did on collapse models was with Angelo Bassi in Trieste. He's the theoretician, and many postdocs who helped with developing these ideas. So this was Mohammed in this case. And the first idea was really to look at the two-level system and say, okay, so if you take now this collapse model series, there should be like a universal noise out there, yeah, and it should affect all physical systems. Now, if you have a two-level system, it should basically shift and broaden the emission of this two-level system. And then if you put in numbers for different two-level type systems, it of course turns out that it is like super, super small, and you can forget to go for it. What is then more successful is to think about mechanical systems, and if you treat them as force noise sensors, so that is illustrated here, you have basically a mass which is coupled with this a spring to an environment, and that is driven by thermal reservoirs. That can be anything, can be gas collisions, can be thermal radiation or so. Then, but also an additional noise source or thermal source would be that CSL noise, and it would basically affect the motion. So you should see excess heating in your mechanical oscillator, and that idea picked up quite a bit. So there people wrote papers and then also did experiments, and there were, of course, existing experiments in low-frequency vibrations of cantilevers and cryostats, which people used for magnetic force spectroscopy. So, for instance, in Leiden, Jörg Osterkamp, he had done this experiment, and we could basically use his data in the first papers to put some bounds on these collapse models. Some years later, and I should mention that the main driver in this experiment is Andrea Vinante. He now has a permanent position in Trento, and he comes from gravitational wave detection with Auriga. So what we did here is basically we have this cantilever and a cryostat, and we built an amplifier. Yeah? So an interesting or important thing to consider and to think about is when you look for like small signals and small noises is how you can amplify them. It's kind of obvious, but maybe you tend to forget it. So in this case, what we did is a sandwich of materials of different densities, which acts as an amplifier for the CSL noise at a specific parameter spot. That is why you see this minima or this plot in the red curve here, and that was particularly designed to test Adler's prediction. So we did this experiment in a millikelvin fridge in Trento, and the red area is basically what was excluded from the CSL plot for this experiment. And then, of course, we had some discussions with Stephen, and because it's only one experiment and he really deeply believes in these models, we agreed to call the statement that our experiment would substantially challenge his CSL values. Okay, so that is the stuff. Then there's the Paul trap. So I'm jumping from experiment to experiment. So that is a European project, a tech project, where we put a Paul trap. It's a blade trap in a 300 millikelvin fridge and trap a single silica particle. So that's a glass bead of 300 nanometer which carries charges. That's a photograph of one of the first traps, which was just maybe a month ago. And that thing here is the Paul trap. It traps the particle with radio frequencies. There's a long story to this. There are many partners involved in a tech project. For instance, there's electronic experts from Frascati who have built a Paul trap electronics, which is super low noise to reduce heating from the electrodes directly. It's optically detected in two different ways with a camera and also interferometrically by homodining. So what we're doing now is we're putting this in a cryostat and then actually looking for the noise. And I think I have one slide which shows where we think that will bring us. So in the best case, we can basically test down almost, there's still 2 orders of magnitude or so, or 1.5 to GRW, but we think that we can push it down here. At the moment, we are somewhere here with this room temperature experiment in the Paul trap. Yeah, okay, good. So there is yet another version of this levitation. So I told you about optical and Paul trap. There's also Meissner levitation, which again has a long history. What we do is we take a permanent magnet, a ferromagnet, which has a permanent magnetic moment, and we use a lead block, which if you cool it below 10 Kelvin or so becomes a type 1 superconductor, and then by the Meissner effect, the field which is generated by this magnetic particle is perfectly compensated, and you can levitate it, and you have a very clean system. So that is from all these different levitation traps. So I told you that it happened accidentally, but it's not true. So of course, all these different traps have different advantages and disadvantages. So this one is the trap which is the cleanest. Yeah, it's low temperature. You have the squid readout. There's no laser. There's no heating. It's very passive, but you cannot change it. Yeah? So you basically define the trap by the cut you make here. Yeah? So how you machine your LED block, that defines basically all the frequencies and everything. And then it is passive and sits there and it's just measuring. While with the Paul trap, for instance, you can move the position and you can change the frequency and you can do a lot of things. So it's much more flexible than this one. The size scale here is tens of micrometers, so it's larger than in the optical traps, and it's how a spectrum looks like. I don't know how familiar you with like mechanical oscillators, so that's supposed to be a super clean spectrum, and we have X, Y, Z, alpha, beta, so different modes of translation, motion, and rotation. And what turns out is that it's an high Q oscillator, so the pressure is 10 to minus 5 millibar, and we already achieve a Q of 10 million, yeah? So 10 to the 7. So that's really good, and if you use something like the force noise equation, which I showed you, you can actually work out that you have in principle that's just theoretically worked out, is not detected so far. That's something which we still have to do, but you have in principle a torque sensitivity of 10 to the minus 20 Newton meter per root hertz, and you have, for instance, a magnetic field sensitivity of femtotesla per root hertz, and so it's an incredibly sensitive system, which is of course opening the path to test fundamental physics, but also applications. So I guess I skipped this here. That's actually some models which we tested. There's, different versions of these collapse models. I don't think there's the need to go into this. The plan is to actually trap particles of different shapes, so disks and rods, and then they have more sensitive motions to test for this noise, and then you can hope to go down to what is indicated as these dashed lines there. I don't know how the time is, but there's, in terms of doing some fun stuff, because you have the system, so you can also look for precession. So if you say you have this particle here which has a permanent magnetic moment and it spins, and now you turn on a magnetic field, then of course it would start to precess. Larmor precession, so that's a macroscopic magnetic resonance experiment, and what this gives you is actually a sensitive tool to measure the magnetic field which you turn on to trigger the Larmor precession. And there's quite some interest with the group of other people to use this for all sorts of reasons. What is maybe interesting, if you again look at what the sensitivity is for the magnetic field measuring, and I don't go through this in too much detail, is still a little bit unclear why that is. But if you make this plot, that's in Review of Modern Physics article from Morgan Mitchell, and you plot all magnetic field sensors, which there are, so that includes NV center diamonds, atomic vapors, quids, and whatever it is. So there's a long list. This is actually the labels of the names, and you see all the magnetic fields versus volume or length scale of the detector is plotted here, and there's this green line, which is called the energy resolution limit, ELR. So there seems to be like a universal, limit that, for magnetic field detectors in a given volume, which you cannot beat, but for some reason our detector, our levitated particle, is by orders of magnitude below this. So I think that's quite interesting. We have to do some experiments to actually prove that that's the case, and then try to find out why that is. And I think I stop with this. All the people to thank, the group in Southampton over the years. So now it's growing again. More people coming in and doing fantastic projects. And I want to thank you for your attention. Yep.
So as usual, if there are people who have burning questions, ask them now. But if they're not burning and demand longer answers, wait for the discussion session. Who has a burning question? Hang on.
Hang on. Microphone.
can you summarize finally when you are planning to get concrete result about this super radiance from the metallic ball?
So we have the results. So we have VC amplification. So what we do is actually not I can tell you just like this, if you don't tell anyone else. But it looks like at the moment, it's a room temperature experiment. It's very simple. It is just a coil which generates the electric field, that's coupled to a Faraday block, and that overlaps with the spinning cylinder. It's the most simple experiment I have ever done. I take the data myself. It takes an hour.
No,
so
how the thing depends, for instance, can you check on the speed?
Yes, so you change the speed.
Etc.
Yeah, so you change the speed, and you do basically, it's an RLC circuit, it's an AC circuit, and you do undergraduate physics, and what you find is that when you spin the motor at a higher frequency than the frequency of the electromagnetic wave, you get a negative resistance.
Okay, thank you.
And you see gain. It's really clear that you see gain in the amplitude of the wave. There's some dissipation in the system, which is not an ohmic loss, and that we have to investigate to really understand what's going on in detail. And that's why I'm hesitant to show you the data and to really make it official. But it is like, I think, a matter of weeks, if nothing, unexpected happens. And that is, I was occupied in the last days. There are like crazy emails going back and forth, so people are really, excited.